Hi, everyone. Welcome to the first lecture of our course. This is an introduction to atomic, molecular, and optical physics. My name is Felipe Herrera. This is a graduate course for the Department of Physics at Universidad de Santiago de Chile. So, in our first class, we will review the basics of angular momentum. Why? Because atoms and molecules and also light in many ways can be described by the physics of angular momenta. So we will see more of this, during the rest of the course. We will see many examples of how atoms can be described in terms of angular momentum, quantum numbers, operators, and wave functions, and how these determine the photophysics and the couplings of atoms and molecules with electromagnetic fields. Also, atomic collisions are described by angular momentum selection rules. So let's begin. Let me briefly review what you probably already learned in undergraduate physics, also your previous graduate courses on angular momentum. So in classical mechanics, we have angular momentum is a vector with well-defined magnitude and orientation. Let's call it L, which is given by R cross P, where R is a position of, let's say, a moving particle with certain mass that moves with some trajectory. And this particle, for instance, could be rotating around a certain axis. And let's call this rotation axis. Let's call the rotation axis the distance to the rotation axis. Let's call it R. Okay, if we choose R to be the origin, and then you have a vector that points to the position of the particle, and maybe this particle has a mass, and we define in the angular momentum, the instantaneous angular momentum of this moving body as the cross product between the position and the momentum, and the linear momentum. Okay, so what is this in quantum mechanics? So we know that linear momentum in quantum mechanics this is basically P goes to minus I h bar, and then the gradient operator. What's the gradient operator? Is there are the first derivatives of any function in space, and in all three orthogonal coordinates in whatever coordinate system we choose. So that means we can basically have a coordinate representation of the angular momentum operator given by this. So it's R cross gradient. Okay, so what is the gradient again? So the gradient operator is all derivatives along, let's say they choose Cartesian coordinate system, then this would be ddx along the position x, coordinate x, dy along coordinate y, and dc along coordinate z. Okay, so this is just a 3D gradient. Of course, we can choose a different coordinate system, let's say spherical, etc. So this is all very basic. Now, what are the components of angular momentum? Components of an angular momentum vector. For instance, what is Lx? Okay, so Lx is going to be, because of the cross product, is going to be ypc minus cpy, for instance, and this in turn can be written as this. ddc minus c dy, and we have set something called atomic unit convention, where h bar is equals to 1, and this is atomic units. So in atomic units, we have that, for instance, the angular frequency is equals to the energy, okay, for example. Now, of course, we can write down expressions, similar expressions for all components. Let's say for y, we have CPX minus XPC. And then for, LC, we have XPY minus YPX. And we can write down expressions, explicit expressions, when we plug in the derivatives along different coordinates. Now, if you can notice that these are the relation between the x's, the y's, and the z's are given by so-called cyclic relations. Okay, so this is a mnemotechnic rule. So you have, let's say, for instance, if you have Lx is equals to Lx goes to y, let's use different colors. If you want the component Lx, then you have Lx is equals to ypc, and then cpy, and then if you want, so you have ypc and cpy, and then if you want lc, then this is xpy and ypc. So maybe I'm not doing this right, but you get the idea. Okay, so the idea is that the indices related to the Cartesian components are related in a cross product according to the Levi-Civita tensor, which is an antisymmetric tensor that basically describes all these cyclic permutations. Okay, so this is, you find all this in textbooks. Is not worth going any deeper here about that. But now what's an important question, right? So what's the question here? So what are the commutation relations? What are the commutation relations for angular momentum components? For angular momentum operators, right? So these are all operators in quantum mechanics. And for instance, you have to recall now the fundamental position momentum commutation relation is, let's say, xpx. You know, explicitly is xpx minus pxx. So this is, we know how to, I'm going to be very explicit here. I know you've seen this before, but okay, so this is new. Okay, so xpx, so this, we know this is equals to I, okay? So why do we know this is equals to I? Well, what you can do, you can express, you can think of this as an operator itself, and then you can act this entire operator onto a function, let's say f of x. And then you have to explicitly write minus I x d dx, and then plus I d dx of x f sub x. Okay, and then let me put some space here. dx of x f sub x. So let's call it f and this of this. Okay, so you first multiply x by a function f of x, and then use product rule to differentiate this, and then you will find out that there are some cancellations that give you that this is equals to I f of x, and so, and this is valid for all f of x, so that means the commutator is equals to I. Okay, and there, and of course you have all cyclic permutations of things like this. For instance, you have ypx is equals to 0, and also cpx, etc., etc. All these permutations are equal to 0 because it's basically a derivative over over one variable, and then you don't have this product rule of differentiation to have this cancellation work out. So you have all this equal to 0 when you have to differentiate something with respect to x along y, and vice versa. Okay. So I'm using the explicit. Of course, you can derive all these from different using purely algebraic arguments, but I'm using functional differentiation because this is what we're going to be using also when we discuss different coordinate systems, especially the spherical coordinate system. So we have. So then we can write. Therefore, we can write what are the commutation relations for, let's say, Lx and Ly. Okay. So we can write explicitly, we can write this is ypc minus, this is Lx, ypc minus cpy, and this is a commutator con cpx minus xpc. And we can then use the commutator algebra to reduce this to something like this. So we have, this separate this bracket, this is an x, okay? So we can write down this like ypc z px, so px minus y pc pc x, and then minus py c c px, then plus py c p z x. Okay, and then you notice that these two things commute because an operator commutes with itself. Also here, so you have that the commutator of Lx and Ly is going to be equals to I minus I ypx plus I pyx, and that's because this thing here is equals to minus I, and this thing here is equals to I, according to this previous result here, and that's equals to I, basically to I LC. Okay. So commutator of x and y gives you z, proportional to z, and the proportionality factor is I. Okay. So we can write down similarly for the other components. Similarly, we have that Ly LC is equals to ILX, again, cyclic permutations, basically. And LX, LZ, LX is equals to ILY, okay? In general, so these are commutation relations for the components. This is what the operators satisfy. Now, this has different physical meanings. So what's the meaning, let's say, of this? Okay, that the z component of angular momentum and the y component do not commute. So if they were to commute, then what we would be able to do is to determine both components simultaneously in an experiment. They will have common eigenvalues. So if you prepare a rotating body in a state with let's say well-known. So I'm going to draw like a classical picture. Okay, again, this is invalid in quantum mechanics, but let's say for the argument's sake, let's keep it. So let's say we can determine the we want to understand what's ill. So then we make measurements, and in these measurements we make a measurement of LC, and we make a measurement of LY, and then we can know these two with some constraints. So basically, if this were to commute, if this commutator was 0, then we will know these two with maximum precision. We can simultaneously. Okay, we can determine them with 0 variance, basically. We can prepare a state with well-defined angular momentum along C and Y. And that will be a good well-defined quantum state. Now, because these do not commute, that basically means because they don't commute, that basically means we cannot know these two components with maximum precision. Okay, so it means we cannot determine the LC and LY simultaneously with maximum precision. In other words, there would be a Heisenberg uncertainty relation associated with this. So then you will work out this in an assignment, okay? But basically, if you write down what is the variance of Ly and multiply this by the variance of LC in any measurement you make about the this rotating body, then this cannot be 0. It's gonna be always lower bounded, this product by a value here, which is the minimum uncertainty. This is non-vanishing, or just say finite. Okay, it's gonna be always bounded by a finite minimum uncertainty. And then you will see in your assignments that this is basically determined by the expectation values of Lx. Okay, so really the 3 components cannot be determined simultaneously. That's all what this means, right? And so you can determine with very high precision where the L vector is along C, but then you know nothing about X and Y, for instance. Okay, that's the physics of angular momentum for all types of angular momentum, not just orbital like a rotation, but also spin. And we will see that later in the course. Okay, so this is a Heisenberg uncertainty principle, that this is kind of the expectation value of the commutator divided by 2 or 4, depending on how you formulate this. You will work this out in detail in your assignments. Now you can generalize this. Okay, you can define what's a generalized angular momentum operator. You don't need to rely on the mental picture of a rotating body. Okay, you can define like a general angular momentum vector operator. For instance, you can define something that we can call J vector, which is an operator in quantum mechanics with 3 components. Basically, it's defined by 3 operators. So we have something we can call Jx operator. Let's put a hat here, and let's put a hat here. Along X, you can have Jy along y. So these are not operator notations. This is just the usual unit vector notation. You can call it I, J, and K, whatever you prefer. Okay, it's just Cartesian components. And then JC operators along C. So this is a vector notation. And why is a vector notation? We will see that all angular momentum operators behave as a rank rank 1 tensor, and rank 1 tensors have 3 components and behave like vectors with respect to rotations. That's why we call this a vector, and this is a vector notation. That's very common. And this is an operator, okay? It's not a classical vector. It's not a Cartesian vector. It's an operator. So the components of this general angular momentum operator, we can define the operator as having this set of commutation relations. So this is JZ, and then JY, JC equals to IJX, and JC, JX equals to IJY. Now this looks like a repetition of what we just said up here, okay? But it is not. Actually, this is very general because these the quantum numbers we'll see later associated with these generalized angular momentum operators, they are not necessarily integers. Okay, so they can describe, for instance, spins that have no classical analog. You cannot describe it in terms of rotating bodies. Okay, so this is very general and is valid for orbital angular momentum, spin angular momentum, light angular momentum, etc., etc. Okay. Now, what are then the question here, if once we define this general angular momentum operator, then what are the eigenfunctions? And what are the eigenvalues? Okay, forget about eigenfunctions for the moment. So what are eigenvalues? What are the eigenstates and eigenvalues? What are the eigenvalues and matrix elements? Of angular momentum operators. Okay, in a basis, regardless of the coordinate representation we're going to describe later, we'll see that in angular space, the eigenstates of angular momentum are spherical harmonics, but we can keep the specific angular representation away for the moment, and we can simply ask ourselves, what are the eigenvalue equations for these operators? Okay, for the J and its components. Now consider first the square of the angular momentum. Okay, consider J square, which is J dot X, J dot J. You know, this is the usual, because the operator behaves as a vector, we can write down things like this, like a vector product, scalar product, and then we work out this, and we have the square of Jx plus the square of Jy. So for actually, now that we all understand that these are operators, let me drop the hats and just write down this. Okay, it's much simpler. We don't keep track of hats. Now it is not difficult to show that J square actually commutes with all components. So this is equals to J square commutes with all components. And this what's the physics of this? What's the physics of this is that you can actually, we will see next class, something called the vector model of angular momentum. So you will see that because J square, if we assume that J behaves as a vector, although it's an operator which might have a very an effective rank in terms of linear algebra much larger than 1. The matrix can be very large. It's actually a non-commuting matrix, basically in an angular momentum basis, because it behaves. The operator behaves as a vector with respect to rotations. We can define something called the vector model. We will describe more. We will talk more about this in the second lecture. But the physics of these commutation relations means that basically, if you define J as a vector, then you know that the length of this vector is basically the square root of J squared. Okay, so basically, let's say you measure J squared. You take the square root of J squared, and that roughly corresponds to the length of this vector. Okay. And then if you measure, let's say this is the z-axis, and then you know what the length of the angular momentum vector is, and you know its component jz, you can know both quantities with maximal precision. So you can set the uncertainty to 0. Basically, you can prepare a state that is both has a well-defined length of the vector, and also a component, you know very well the component of this vector along one axis, okay, one axis only. And that basically tells you that you're basically using, in this case, in this example, that J squared commutes with JZ. But then if you know J squared and JZ, you know nothing about JY and JX, okay, because JY doesn't commute with JZ, and JX doesn't commute with JZ. Okay, so you cannot determine all 3 components plus the length. You can only know the length and one component with certainty. That's the physics of this. And so then the operator commutes. We can define simultaneous. So that means that we can define simultaneous eigenstates of, let's say, J squared and JC. So these will be 2 commuting observables. And in general, we can do this for any pair. Okay, let's say J squared and JX. I can also know with certainty this. So I can know simultaneous observable of these, or this, or this. Now for concreteness, let's consider the J squared and JZ. Let's use J squared and JC. Okay, these 2 operators from this commuting set, and since they commute, they can have common eigenstates that we're gonna label by common eigenstates. We're gonna label them by Jm. Okay, so what are the eigenvalue equations here? So we wanna write down J squared over Jm is equals to lambda J, okay, of Jm, and Jz of Jm is equals to m Jm. So what are the eigenvalues? This is just a notation, right? So what are lambda J and m? So for the moment, they're completely general quantum numbers. So one associated with each one of the labels here. So quantum, we associate 2 labels, two labels for the eigenvalues, for the common eigenvalues on the state. That's how we label these angular momentum states. So we have 2 equations for them. Now, what are the relations? So So what are these? And what are the relations? So are they bounded or unbounded? How do we determine angular momentum algebra from these very basic relations? Now consider this. Consider the eigenvalue equation. Let's say JC square of JM according to this is going to be equals to M squared of JM. Okay, and then JC squared, if we recall the definition of J squared, then JC squared is going to be J squared minus JX squared minus JY squared JM, and this is equals to M squared JM, which means that JX squared plus JY squared on JM is equals to lambda J minus M squared. So what does this equation tell you? Now, what do we learn from this? So because this operator is a square of an Hermitian operator, then we must have and the norm of these states is unity. Then we must have that this thing has to be positive. Okay, that's the first thing we learn. Okay, that's because this is the square of an Hermitian operator, and Hermitian operators have real eigenvalues. So the square of a real eigenvalue is a positive number, and that means this has to be a positive number, which implies that M squared cannot exceed J, lambda J. So that's why this is a constraint. Constraint on M. Okay, that's it. First thing we know. So if M squared is bounded, so if M squared is bounded from above by lambda J, that means that M itself has to be bounded between a minimum and a maximum value. Okay, a minimum and a maximum. So that's the other thing we learned. So what are the allowed values, right? So that's the next question, right? What are the allowed values? For M. Now to understand this, let us introduce the so-called raising and lowering operators. Raising and lowering operators. Now, and these are denoted conveniently by J plus. We're going to define them as Jx plus I Jy. Sorry, this is Jx. And the J minus is equals to Jx minus I Jy. Now, because you know the commutation relations between the different components of J and also J squared with the components of J, then you can derive commutation relations of things like this. So you have J squared commutation with J plus minus that's going to be equal to 0. okay, because j squared commutes with both of these components, and then you can also you also have that JC doesn't commute with the raising and lower operators because it doesn't commute with the components of x and y. So, but it's going to be given by this, basically the commutator, and the raising and lower operators themselves do not commute, but instead they give you something that's proportional to JC. Again, because of cyclic commutation relations. Now, the other thing to note is that these two operators are non-Hermitian. Okay, these are non-Hermitian operators. They're actually related, right? So so let's say J minus is equals to the Hermitian conjugate of J plus and vice versa, right? Now let's consider this function, okay? Now that we introduce the raising and lower operators, consider this function. Then we're going to J plus minus of Jm, okay? This is a valid eigenstate. Is the action of an operator over an angular momentum state, and we can write down things like this. So what is J squared on this wave, on this state? What is this J squared on this state? And because these two operators commute, so recall this commutation relation, because J squared commutes with J plus minus, I can flip the operator order and then have something like this, J squared of Jm, and this is going to be equals to lambda J of J plus minus of Jm, right? Which means that this wave function here is also an eigenfunction of J squared. Eigenfunction of J squared with the same eigenvalue of Jm, with lambda J eigenvalue. Now, we also have this relation, huh? Consider now this relation. JC, how does JC act on this function that we're proposing, this state that we're proposing, on J plus minus of Jm? And here we're going to use this other commutation relation, and we're going to write down this in a different way. So we're going to use plus minus J plus minus, and then plus J plus minus of JC over J, acting over Jm, which is rewriting the product here, and the result is M plus minus 1 of this function, of the original function, J plus minus Jm. Okay. So we can write this. So we can write. So what do we learn here? What we learn is that this new function here has the same component m of the c component of the angular momentum, has the same eigenvalue m plus or minus 1 according to whether you raise or lower the number here. Okay, according to whether you use the raising or lowering operator. So we can write, J plus minus acting over Jm as a constant that we're gonna call C plus minus, and returns the same, the tensor state with the same value of J, because it shares the eigenvalue lambda J, but has a different value of M. So now M of the new state is M plus minus 1. Okay. So it raises or lowers M by 1 value. Okay. Then there is a, what's the minimum value of M? So then, what is the minimum value of M? Must have that J minus over J M minimum has to give you 0, right? Because if M is constrained and J minus lowers the value of M by 1 unit, therefore, if you're acting J over the minimum, it has to give you 0, right? And also you must have this a similar thing for the maximum value, right? So J plus of J M maximum also has to be equal to 0. So you have to satisfy this constraint. And of course, you can use this to write down any relation you want. For instance, you can multiply the first relation here. You can rewrite it like J plus J minus of J M minimum equal to 0. And also you can write down J minus J plus of J M maximum equal to 0. Okay. So why do we write these products? Because now we can use things like this. You can use a relation, which you can easily prove, that J plus J minus is equals to J squared minus JC squared plus JC. Plus JC. Let me change the notation again. Plus JC squared minus JC squared plus JC. Okay, you can prove this. It's not hard. You just use definitions of J squared and the commutation relations of J plus and J minus to arrive at this. That's one way to write down these relations, and this is equals to basically J squared minus JC, and this is JC minus 1. And you can also write J minus J plus is equals to J squared minus JC times JC plus 1. Okay, so these are two key relations that you can derive just using the definitions. Okay, just using definitions and commutation relations. If we then replace these two expressions, this and this, if we replace them here and here, then we get the following. Okay, then we get, for instance, that J minus J plus acting on Jm maximum is gotta be equal to 0, but then this also has to be equals to lambda J minus M maximum times M maximum plus 1. has to be equal to 0. Why? Because we used this relation. Okay, we use this relation. On the other hand, we have that j plus j minus of j m minimum is equal to 0, and that using this relation means that this has to be equals to lambda j minus m minimum, and this is m minimum minus 1 also has to be equal to 0. Now you can equate, you can eliminate lambda j, equate these two relations, and arrive at this. Okay, you can rewrite this in the following form. You have m maximum plus m minimum times m maximum minus m minimum plus 1. And this has to be equal to 0. Okay, all I'm doing here is equating these two relations and eliminating lambda j. And then rearranging terms a bit. Then you arrive at this expression with these two products. But this is not possible, right? So this is not allowed. Why? Because we said that that m maximum has to be equals or greater than m minimum. That's a constraint, right? So this is not allowed, which means that m maximum has to be equals to the negative of m minimum, and that's another constraint we found on the m's. Okay. Therefore, we can set, and this is we set by hand. Okay, I'm gonna put it by hand. We set by hand that because of this relation, we must have that m maximum minus m minimum is equals to 2 times j, where j is an integer or half integer. Now, at the level of non-relativistic quantum mechanics, this is actually, we cannot derive this. We have to go to quantum field theory to prove that this distance between the minimum and maximum j can actually be written by this, where j could be either integer or half integer. Okay. So in other words, j could be equals to 1/2, 1/3, etc. Right? Now we conclude. Then we must have that m then, m maximum, we can assign it to j, m minimum equals to minus j according to this relation, and therefore m is bounded like this. Okay, m goes from j to minus j. Okay, we've derived this. Derive in quotation marks because we have to define that the relative distance between the distance between the minimum and the maximum value of m is equal to 2j, where j is a half integer or integer number. Okay, and that gives us this. This is the usual range of allowed values for m, which is the azimuthal quantum number that you saw in the hydrogen atom. And if you saw rigid rotor, you also saw this. But now we have derived it, quotation marks. Okay. Now, therefore, we have 2j plus 1 possible values of m, which we call the projection of the angular momentum vector j along the Z direction. Okay. Now, what is the value of lambda j? Now that we have, let's go back to this relation. Let's find any of them, right? We can use any of these. Now that we have what the M minimum value is, for instance, then we can derive an expression for lambda j. So what is lambda j? So then we have, for instance, that this relation M minus M minimum minus 1 equal to 0, with M minimum equals to minus j, gives us that lambda j is equals to j times j plus 1. So these are the eigenvalue of j squared. The square root of this is the length of the angular momentum vector. We will see that in more detail next class. Now we have constrained the values of the quantum number m. M can take integer or half integer values that goes from minus j to j, and then the eigenvalue of j squared is also determined by the same integer or half integer value j. And now there is one thing that we haven't defined. There's one thing left to define. So what is this constant? Okay, what is this constant c? So we have c plus minus. Remember, we have, that's the question we have. So what is the constant c plus minus? So according to our definition, we have the operator j plus minus acting on j and j. Sorry, just jm is equals to c plus minus jm plus minus 1. Okay. So, and we also know that jm is normalized. So we have, because this is normalized, we can write down that the norm of this function is c minus plus c plus minus j minus plus j plus minus of jm is equals to c squared, c plus minus squared. And because we have expressions for these products, okay? The expression we're going to use is basically, sorry. So we have c plus minus squared. This is basically, we can rewrite this operator product like this. We can say this is equals to j squared minus jc, jc plus minus 1 acting on jm. Okay, and then because we know jm are common eigenstates of j squared and jc, this basically tells us that c plus minus squared is equals to j plus 1 minus m plus minus 1. Okay, but we have only determined the absolute magnitude squared of c plus minus. Okay, and we did this because the states are normalized. So we say that this is state jm's have unit norm. So that's the only thing we used. And we use commutation relations to arrive at this. But that gives us an ambiguity. The ambiguity of the face of this number c. Okay, so now there is a phase ambiguity. I can basically write down c plus minus, transform it to any complex times c plus minus, and I'll get the same result. Okay, I get the same result here. So how do we choose the phase? Okay, now when there is an ambiguity in physics, we resort to conventions, and conventions are introduced by notable colleagues, and there is a convention by I think Edward Condon. So there is a Condon convention, which is widely accepted. Okay, is assume that all these C plus minus are real numbers. Okay. So phi equal to 0. Okay, that's the phase convention. It's simplest one, right? It's the simplest one. It's not the unique convention. Some people use a pi over 2 convention. So this is a purely imaginary number, and that complicates a lot of things when you work out with the functions themselves, with eigenfunctions with spherical harmonics and the conventions for spherical harmonics. Now the safest route is to assume that all these quantity is real. So you have really that C plus minus is equals to the square root of j plus 1 minus m plus minus 1. Okay, and there you have, and now you know how these ladder operators, these raising and lowering operators act on angular momentum eigenstates. Okay, so you have all the matrix elements you want. So now you can write down matrix elements in the Jm basis. You can write them down for this. So this is J squared. You can, of course, there are some delta functions. You can write down Jm for Jc and any component, J prime, J prime. These two functions, these two operators are diagonals. And then you can also write down now Jm of J plus minus. And these are off diagonal. These are non-diagonal operators. Okay. Using your knowledge of how J plus minus operators act on angular momentum eigenfunctions, then you can, for instance, write down things like this. What is Jx? Okay, of J prime and prime. And now for this, you need to use the fact that Jx is basically like J plus J minus. And you know how J plus and J minus act on angular momentum states. Also, you can know what the component Jy is. Right? Good. So we know. So we've defined general angular momentum operators. We have established what are the quantum numbers associated with them when they act on angular momentum wave functions that we have labeled like this. Okay, this is all linear algebra. We haven't said anything about how these states look in coordinate space. In coordinate space, meaning not necessarily Cartesian space, but most primarily angular space, okay, polar coordinates. We introduced these raising and lowering operators and how they can be used to derive relations between J and M. Okay, and this we do here. We introduce the notion that J is an integer or half integer quantum number that we're going to call the angular momentum quantum number, so that M is constrained between minus J and J. And also the eigenvalue for J squared is equals to J times J plus 1. We introduce a Condon convention for the raising and lowering operators. We also defines the convention for the phases of the X and Y components of the angular momentum. Now, I think with this, we're going to end this lecture. It's been an hour now. And then in your assignment, number 1, you will explore more about angular momentum wave functions. And what are the angular momentum wave functions? We need a coordinate space, and a coordinate space in our case is angular space. So in polar coordinates, we will use the, we will see that the angular momentum wave functions are spherical harmonics. How? Well, we will write down actually this eigenvalue equation in polar coordinates, spherical polar coordinates. And you will see that this results in a, this results in a differential equation. Okay. That's well known in mathematics, in applied mathematics. And the solution of this differential equation are the spherical harmonics. And the, in particular, the associated Legendre polynomials that relate to these spherical harmonics result from the differential equations for each of the variables theta and phi when you do separation of variables. And you will learn about normalization conditions and also phase conventions for the theta functions, for the spherical harmonics in the theta coordinate. Okay. Now with this, I want to end the lecture now, and we will meet next Tuesday. Okay, this Tuesday, and we will see next class more about the vector model. Okay, this class we will learn more about the vector model, which is very much used in chemistry and physics to do some hand waving and presentations, and also to derive some new results. Okay, it's been used in the past to actually do physics. The vector model of angular momentum. So with this, thank you very much, and see you next time.